Hello, I'm Dion Jacobs, and together with my colleague Mata Sayer, we have the pleasure to be able to propose to you the work of the Process Systems Engineering student team from the AVT at the RWTH Aachen University, consisting of Yannick Bote, Johanna Güttler, Jan Pauschek, our advisor Kanka Asulu, and of course ourselves. Because of our performance and pleasure to win the EURECHA Student Contest Problem this year, we have the honor to be able to present to you our process design proposal. It's no secret that the world is in a climate crisis. Last year alone, 36.7 billion tons of carbon dioxide were emitted worldwide. And without any significant change, this number is only set to grow. The chemical industry has already started to play a very key role in fighting the climate crisis, specifically via renewable energy utilization and carbon dioxide utilization. However, both of these fields are still facing key challenges, specifically to be able to integrate intermittent energy sources with steady state processes and to be able to efficiently change the oxidation level of carbon. Because these are two such relevant problems within the industry, the EURECHA Committee, as well as its sponsors, set the problem of this year's EURECHA Student Contest to be exactly those, to be able to find a process design challenge which best solves both of these problems. And that's a challenge which the students at the RWTH Aachen eagerly uptook. The rest of this video will be us introducing our process design proposal while as well trying to propose to you a process which is economically, ecologically, and thermodynamically efficient as possible. We begin our process design with the systematic screening of products and processes. We take our three key main factors and design 7 key performance indicators, which allow us to evaluate the potential of processes found in literature. These key performance indicators are given relative weights of importance derived from a pairwise comparison matrix which we created, and then use those to evaluate the processes. For each process, product, and key performance indicator, we define the potential of the process and product via a fixed quantitative range. And after a weighted sum, we are able to determine the estimated potential of each process found in literature, which should then be investigated for our possible process design. When investigating all of the most highly rated processes, in a eureka moment, we realize that 2 of our processes, co-electrolysis and sorption-enhanced DME, both share a key chemical stream, that being of syngas. And using this realization, we came to the decision to develop a novel dimethyl ether production route, which combines both of the process into one combined process. Interestingly, when reevaluating this combined process with our systematic screening method, we see that it is the most highly rated method and process amongst all of those investigated. Now, what does this process look like? Well, starting with the building blocks, we take raw material of carbon dioxide and water, as well as renewable energy, and send it to a co-electrolysis cell, which enables us to produce syngas. This syngas is then fed to a steady state sorption-enhanced DME synthesis process, which produces our dimethyl ether. And while this allows us to utilize carbon dioxide as a raw material, it fails to account for the intermittent nature of renewable electricity. Therefore, we decided to instead implement a reversible solid oxide cell, which either allows syngas to be produced from CO2 and renewable electricity in an electrolysis cell mode, or to take pre-produced syngas and consume it in a fuel cell mode to then also be able to produce electricity and raw CO2. This decision to implement a reversible solid oxide cell allows us to dynamically and reversibly change our production rates to be able to incorporate the intermittent nature of electricity. However, the exact implications of this process decision will be discussed later by my colleague Matas. Now, when developing research and doing a process design proposal, it's always nice to be able to go more and further beyond than just what the literature proposes. And for our process, that was no different. One step and potential for innovation which we brought into our process design proposal was in the modeling of our reversible solid oxide cell. We simulated our reversible solid oxide cell within Aspen Plus. However, when you look at it into the literature for being able to simulate such a process, we see that the electrolysis cell and the fuel cell mode are always put into 2 separate process models, sometimes also including different unit operations. So it was our goal for this process to be able to come up with one agglomerated and coherent process unit our process model, which allows us to simulate a reversible solid oxide cell in either mode without needing to switch into different units and models. This is important later for our optimization, and we managed to accomplish that by agglomerating process designs and taking advantage of the two key reactions which occur within the reversible solid oxide cell, that being the reverse water gas shift and the electrochemical water splitting. For our absorption-enhanced DME synthesis process, our innovation comes in the form of the reactor block which we implemented. As opposed to just using a standard methanol dehydration reactor, we decided to, as stated, implement a absorption-enhanced DME synthesis reactor block, which enables us to in situ remove water via an absorbent bed. This takes advantage of temperature pressure swing reactors, which however are not able to be simulated and run in a steady state process. So, taking work completed by many papers in literature, we developed custom model simulation within MATLAB, which we then use to export the improved conversions over to Aspen Plus and thus be able to create a steady state absorption-enhanced DME process. To be able to evaluate the potential and the effectiveness of our process, we took a case study based in the country of France. Now, the two most important conditions for our process when considering a case study is the availability of renewable electricity and that of carbon dioxide. Looking to the availability of renewable electricity, we see that France has a wide variety of high energy density locations from which we can derive our renewable electricity. However, cross-referencing that with the large sources of carbon dioxide, we see that there's only two real choices, in the north or south of France. We decided to implement our process in the north of France, specifically in Dunkirk, where we see that an offshore wind park and a carbon capture facility is planned for the year 2025. Based off of this location, we developed the process design goal for ourselves to be able to constantly produce 35 tons per hour of DME from captured carbon dioxide. So we have a process design, we have a boundary case, we have a case study, and we have the process design goal. But that still leaves a lot of questions open. For example, if we look at the right half of our process, the absorption-enhanced DME synthesis, we ask ourselves, well, what should the inside of that process look like? What specifications should the unit operations have? And as well, what kind of feed flow rate do we need within our process model to be able to produce the 35 tons per hour? To be able to answer that question, we decided to do a process-wide plant optimization. Now, plant optimizations are challenging because you're working with nonlinear, non-convex functions. You have mixed integer variables and expensive derivatives, which may not always be present in the case of a black box formulation. To be able to solve this kind of problem, we need some sort of global derivative-free solver for MINLP problems. And to be able to solve that, then we chose a genetic algorithm optimizer. Taking a small portion of our SEDMES flowsheet, we allowed the genetic algorithm to then set process parameters for each of our unit operations within the process, within our flowsheet, trying to always improve the net present value. Whenever a selected point of the genetic algorithm leads to the process model being infeasible, or in our case, where Aspen Plus is not able to converge the process model after multiple iteration attempts, we add a hefty penalty to the net present value fitness to ensure that the genetic algorithm stays away from any such infeasible points. In the end, our genetic algorithm came up with an optimal operation after just 14 generations or 560 iterations, which fell within our optimality tolerance. This ended with a absorption-enhanced DME process of being 121, or with an NPV of 121 million and a required feed syngas flow rate of 3.1 tons per hour.
Now that we have identified an optimal operating point for the SEDMES process, we want to focus on the RSOC process and how to produce a continuous 3.1 tons of syngas per hour for the continuous SEDMES process. And of course, the simplest way of operating the RSOC process would be to constantly operate in the electrolysis mode to provide syngas. However, when we also take electricity supply into account, it becomes clear that it can make sense to operate in the fuel cell mode for two reasons. First, when the electricity price is so high that it doesn't make sense to produce and sell electricity. And secondly, when the electricity availability is too low for us to provide, or too low to provide the electricity for the SETMIS process, so that we have to provide this electricity by ourselves. To better understand our models and process behavior with respect to changing electricity price and electricity availability, we developed within our case study 3 scenarios. And the first scenario is what we call the wind park scenario, where we have a contract with a wind park and therefore a constant electricity price, but changing electricity availability. In the second scenario, the electricity network scenario, we purchase the electricity from the grid and therefore face a changing electricity price, but constant electricity availability. And in our third scenario, the constraint scenario, we include both the changing electricity price and the changing electricity availability. So how does the underlying optimization problem look like? We want the solver to tell us for every hour in a year, for a given electricity price, that is the upper curve, and the given electricity availability, the lower curve, should we operate in EC mode or in FC mode, and how much syngas should be produced or consumed? And we translated this idea into a MILP optimization problem that we implemented and solved in GAMS. In this problem, we optimize for the NPV of the combined process, subject to constraints such as the mass balances, electricity availability, and economic equations. And the solver delivers highly interesting and very traceable results, and we want to present the results for one specific day in the wind park scenario. The wind park scenario, just as a short reminder, means constant electricity price and changing electricity availability. On the right of the figure, we see that due to this constant electricity price and sufficient electricity availability, there's simply no incentive for the process to change to the FC mode. However, in times where electricity availability is very low, the process or the solver would choose to produce electricity in the FC mode. These are only the results for a single day. If we consider the whole year of 2021, we see that in the optimal operating regime, we would be operating in 64% of the time in EC mode and 26% of the time in idle mode and 10% of the time in FC mode. Now that we have optimized both the SETMIS process and the RSOC process, we want to evaluate our process ecologically, thermodynamically, and economically. And for that, we have conducted an LCA and computed the exergetic efficiency and the break-even price of our process and of 2 reference processes. And the first reference process is a state of technology process, where we produce DME from natural gas, and the state of research process is a DME process from biomass. To start with the life cycle assessment, here we performed a life cycle assessment with the cradle-to-gate assumption, and we used the open source database GREET. A very important second assumption concerning the life cycle assessment is concerned with the byproducts. Our process, besides providing DME, also produces significant amounts of oxygen and electricity. However, our reference processes don't. And therefore, we choose a system expansion approach and include the most likely conventional ways of producing oxygen and electricity also in our reference process. This allows us to fairly compare our process with the reference processes. The results show that our process, in terms of greenhouse gas emissions, outperforms the reference processes, and we also see that we have a higher sensitivity of the scenarios or to the scenarios for our process. And the reason for this is that we use a lot of electricity as energy supply, and since in the different scenarios the electricity supply comes with different grid mixes, the greenhouse gas emissions change. For their exergetic efficiency, we computed or we considered both the material streams and the energy streams after heat integration in Aspen Energy Analyzer, and we divide the exergies of the product streams by the exergies of the input streams. And again, the results show that our process is competitive with the biomass process and also with the natural gas process. The efficiency of the wind park scenario and the constraint scenario is a little bit reduced, because in these scenarios we operate more in the FC mode, which comes with an additional conversion step from CO2 to syngas back to CO2 and electricity. And finally, we evaluate the economic performance of the three processes by comparing the break-even prices. And for our process, the break-even price is 2.14 euros per kilogram DME. And in the results, we see that once again, our process is competitive with the biomass process, although in overall, the prices are still much higher than the current market price. As an overview for this evaluation section, we can say that our process outperforms the reference processes in terms of ecological performance and thermodynamic performance. However, in terms of economic viability, we are still lagging behind. However, we do see a good chance for our process to become economically viable in the next few years, because in our conservative estimation, we didn't consider carbon certificates and also not a future reduction in the costs of electrochemical cell equipment, for instance, and also not very volatile natural gas prices as we observe them in the moment. To conclude, in our work, we proposed a novel DME production route from CO2 tailored to the use of intermittent renewable electricity. We also modeled, simulated, and optimized the process as part of a multi-scenario case study. And finally, we demonstrated the process ecological, thermodynamic, and economic potential. Thank you for your attention. And here are our references.